Start.
Thanks for coming. Thank you for having me. My name is Pedro. I work for Protocol Labs. In Protocol Labs, we work to make the web, decentralized web, a reality. We're the makers of several open source projects, namely IPFS, and also Filecoin, and a bunch of other surrounding projects like Leap Peer-to-Peer, IPLD, multi-formats, and a lot of others. I'm a software engineer, and also I am the leader of the Dynamic Data and Capabilities working group on IPFS. Here, we try to research and enable developers that are building decentralized web apps, providing them solutions for identity, access control, collaborative, real-time data, and also offline access. Today, I'm here to talk to you a bit of my history, my story around data loss and conflicts. So let me take you on a trip back to 1998. I was fresh out of university, and at the time, just for your reference, for those that weren't really aware around that time, internet was just dial-up. Java wasn't a big deal, and open source was really something that was starting to become relevant. So most of my projects for customers use Oracle database, one way or the other. And on my pet projects, I use MySQL and some PHP to detox myself from all the C++ and Java. So let's see how this system handle conflicts and data loss. So let's say that we have two users and one database. Okay, so database has this record, and the two users fetch this record. So let's say that they're editing this record over a form, web form, for instance. So they load, each one of them has a browser, and they load the document on their browser, and they make some changes. So this stickman changes the document to A, the other stickman changes the document to B, and then the first user hits the save button, so the document travels all the way to the server. The database server accepts it, saves it, document A, and then the same thing for the other user. Hits the save button, document is saved on the database, and then what happened? So that user overwrote what user A had written, but user A doesn't know about that. It is not aware that user B overwrote his data, so he's left confused or ignorant, and user B has won. So this is, last right wins conflict management policy, which is really not a conflict management policy. It's just something very, very primitive, and this makes me really, really, really sad. So a bit later, 2009, Node.js came about, and with that, the NoSQL movement started emerging. So a bunch of alternatives to SQL data stores like CouchDB, Redis, MongoDB, and Cassandra, and some others. And it freed us, being JavaScript and document-based, freed us from the shackles of relational data. And one of those products that was really important to me at the time was CouchDB. For those that don't know, CouchDB is a document-oriented database. So it's not a table-oriented database, it's document-oriented. So the record is a arbitrary JSON document that can be any JSON document. The database has an HTTP interface, like a RESTful HTTP interface, and has a permanent changes feed. So you can observe all the changes that a given database is suffering, okay? And also a really interesting thing is the concurrency control. That's why in the logo you had, this doesn't show here, but the motto was, you can now relax. It means that you can now stop worrying about concurrency or losing data. Let's see how it did that. So each document has an embedded sequential number that's monotonic, it's always increasing with saves. okay? And when you write a new version of the document, you specify which version that you're basing that write upon, right? So let's see an example here. So CouchDB has a document, has already the document on version 1, and then the two users, or two stickmen, load the same document on their side, and they both make a change, a concurrent change. User A saves the document, hits the database first, and so since let me backtrack, that version 1 is the same as the current version, it accepts the change and saves, and it creates a new version, so version number 2 of document, which contains the value A. And then user B saves the document, and the version 1 is smaller than the current version, so it doesn't work, and so his request is denied. Okay? What it has to do, either stop there and say, sorry, you're out of date, just refresh the page and edit again, or if the software is more smarter than that, it can do something that is fetching the document, having both the current version and the user-edited version. It can somehow merge the two documents, the changes on those two documents, and then save back that document again, creating so database checks whether the version is the same. So we had like version 2, accepts the change, and then saves version 3, which is the merge result. Okay, so client-side merge conflict. So let's see how this works with CouchDB availability. So you can either have one server, or you can have more than one server, and you can do async replication between any two databases. So they replicating the changes asynchronously between each other in both directions. So what's the expected behavior here? So let's say that you're writing here. How can you read your write? So how do you make sure that the thing that you're writing here on the next request, you will be able to read immediately? So you either wait for the replication to propagate, which is hard to figure out, or you use the same instance that you wrote on. Okay. So what guarantees does it bring? So there's a deterministic conflict resolving. When two users are editing the same document here and there, and the replication is working, the thing is that if there is a conflict version, the database, both databases will pick one of the versions in a deterministic way, right? But one of them will win, okay? And then the user has to poll for conflicts, has to ask the database, are there conflicts for this document or in the changes feed, and be aware of them, and then try to and solve them. So it can get all the conflicting versions and then resolve them the same way as we did before. I call this one of the right wins. And the conflicting documents can be extracted and then merged again. CouchDB is a JavaScript version of CouchDB, runs on the browser and also runs on Node.js, and can also sync with CouchDB. So it's a document database that you can have on the browser, right? So here you have like the model. They have a bunch of users on the browser. There's the CouchDB, and it can be used to sync with a central CouchDB server. That's one way of doing it. So the cool thing here is that the data writes are local, right? So they're highly available because they're local, and they're really fast, right? And they're eventually synced to other peers via the backend server, so the CouchDB. So when someone makes a change here, it's propagated here, and then the others get that change, right? So conflicts should be handled at the client level, so to prevent data loss. So really, what we did here was create a bigger problem and push the merge problem further up the stack to the client. So the concurrency semantics is the same, but on the client and on a larger scale, right? So if you want to have the data local, I think we have to solve this problem, all right? Also, the way that you model your documents is really important to the way that you're going to merge two documents. Okay? So you cannot have like arbitrary JSON documents and then decide how to merge them ad hoc, because you'll probably lose some data. So you have to be really careful how you design the schema of your documents. There's another option on the NoSQL world, which are the Dynamo-like databases. One of them is React, and the other one is DynamoDB. I think there are others that have the same functioning principles. They were eventually consistent, much like CouchDB. So when you do a write, you write to as many instances as you like to guarantee that your write will be persisted. And they detect conflicts as the nodes talk to each other behind the scenes, all right? And they know which version of each document each one has, and when there are concurrent writes, because you wrote a version of a document to one server and another customer wrote a conflicting version to another one, when those two are in conflict, they are emerged to the user. So when next time you query that document, instead of getting one value, you'll get two or more values because the database doesn't know what to do with them. I have two conflicting values. Please solve them for me. So I don't know about you, but I really hate conflicts. And I was asking myself, is there a way to automatically solve conflicts with a reasonable semantics and safety? So you can do a meme and say, like, small brain, like losing data, and then detecting conflicts is the next level, emerging conflicts is the next level, and now I will really like to avoid conflicts. Okay? Hello to CRDTs, which are conflict-free replicated data types. It's a really long name for something that is really simple. It's a principle that was formally defined in 2011, and ever since has been a really active research field. So CRDTs provides not only eventual consistency, they provide strong eventual consistency. And let me explain what that is. So on top of everyone agreeing on a final result, they also guarantee idempotency, which means that the order of the messages can be delivered more than once to any of the peers, and to any of the databases. You can have commutativity, so the order of the messages can be swapped. And you can have associativity, so you can pair messages and send them in one go, in somehow join messages, okay? Associate messages. This means that you can decentralize communications between the peers, and you can form a mesh between peers. And you can have an unreliable delivery of messages, and you can still, using CRDTs, guarantee these safety properties, okay? So the system model that I'm going for is loosely connected. Doesn't really show, but there are some strains here connecting some of the dots. So a loosely connected network. Not all of the network nodes talk to all the other network nodes directly, but they can all reach, much like the internet, they can all reach each other eventually, okay? And they have a bunch of messages traveling around, all right? So this one is propagating changes made here, that one is probably propagating changes that were made there, but it all works somehow. It all works, even if messages are being lost or reordered along the way, okay? So CRDTs are not a library or a specific data type. It's more that it's a mathematical framework that allows like a common language to talk about concurrency, convergence, and safety, okay? But yes, you can have many different specific CRDT types, like counters, sets, maps, arrays, JSON documents even. And for each one of them, you can have different variants according to the semantics of how you solve conflicts, right? For instance, you can have a set that when there is a concurrent write and a concurrent remove, the remove wins or the write wins. So you have a write, win, observable, remove set, and all there's dozens of these types that are defined almost daily by academia research. And not only that. So there are like two super types of CRDTs. One is operation-based, which has different properties than I talked about. The other is state-based, which is what we're going to talk about. And a very close cousin to this, which is delta state-based CRDTs. On state-based CRDTs, each message contains the entire state. So peers talk to other peers, exchanging messages, and the messages contain the entire state. Let's see what the state-based CRDT looks like. Very simple definition. So there's an initial state, internal initial state. There's a bunch of mutators, so functions that change the state, and they return a new state, right? And there's a merge function that gets two states and returns a new state. And there's a value function that gets a state and then returns a value. For instance, if the CRDT represents an array, this is how you get that array out of the state, okay? So a quick example would be a grow-only set, which is a set that can, the members can only grow. You cannot remove members. So initial state, empty set. Mutators are adds. You can add an element and returns the state with union with the element itself. A merge function that is also the union of both states, which are the sets, and a value function, which is the state itself, because the state is already the set. So let's see how a network of 3 peers would work on this. So peer 1 to 3. Let's say that they start with each one adds locally an element to the set. So peer 1 adds element A, peer 2 element B, peer 3 element C. Peer 1 sends a message to peer 2 with his state, which is a set with one element A. So peer 2 adds that element to the set because it makes a union of the set. Then peer 1 receives a message from peer 3 containing the state, which contains the element C. And then node 1 adds that to the set, internal set. And then peer 2 sends a message to peer 3 with his set. This enables peer 3 to get B and A, adding it to the set. And then peer 2, for instance, talks to peer 1 with B and A. And then peer 1 joins both of the sets and then gets A, C, and B. And then you can have like a final message from 3 to 2 that makes the state be all the same. So if it's an unsorted set, they are all in sync. They have the same elements on the set. Okay? Another example, this is kind of cheating, right? So grow-only sets is a cheat because the state is the set itself. Let's see a bit more complex example with a grow-only counter. A grow-only counter is the counter that can only go up, can never go down. And you can use that for instance, counting likes or counting stars, counting views on a certain resource. So the grow-only counter starts with a map. The state is a map, and mutators are bound to the node identifier. So here I'm introducing something which is called a node identifier. Each replica has one identifier, and when I increment the state, what I'm saying here is that I'm returning the map of the state with the element that belongs to my replica incremented by n, which is the argument I pass here, which defaults to 1. So I'll show you an example which is really simple. And the merge function is a point-wise maximum, which means that for each common point in both the states, I'm going to get the maximum one of them. So if I get 2 On peer A, I get 1 and 2. Maximum of 1 and 2 is 2, so I get the 2 at the end. And the value function is the values of the map. So let me exemplify that. So let's say that we have 3 peers again. Each one of them has a slot in the state for each one of the other nodes. So peer 1 has the 1, 2, 3 slot, and vice versa. And let's say that they start with, so peer 1 starts with a counter of 2, peer 2 with a counter of 3, and peer 3 with a counter of 1, and now they want to agree on a final value. Okay? So the first thing that peer 2 can send a message to, peer 1 sends a message to peer 2 containing the state, which is 2, 0, and 0. Okay, so peer 2 incorporates that state. The maximum of 0 and 2 is 2. The maximum of 0 and 3 is 3. Maximum of 0 and 0 is 0. And then peer 3 does the same, sends the current state. So now peer 1 is going to incorporate that message there. And then peer 1 communicates to peer 2, incorporates the maximum here is 1 here, but here the maximum is 3, so it keeps this value. Okay? So 2 talks to 3, sends the entire state to 3, and then 3 can update the state, and then 3 talks to 1, 1 updates the state, and then the value is the sum of all the values in the map. 6 here, 6, 2 plus 3 plus 1, 6, 2 plus 3 plus 1, 6. So they agree on a value which is 6. Okay? It's clear? All right, so let's make some live changes on this. So let's say that user, now that they agree on a value, let's say that a user calls increment here, and calling increment here mutates the internal state to 2. So this is the entry of 3 is incremented to 2. Before it was 1, sorry, 1, and then 2. And then at the same time, a user increments it here. So instead of 2 at the slot 1, it will be 3. And now, for instance, node 1 sends a message to node 3, 331. The maximum, pointwise maximum of 331 and 232 is 332. So that's the value that he'll get, 332. Okay? And the same on the other way. I'm going to send 332, and then the maximum will be 332 here. So they are both in sync now, okay? And then they can do the same at the same time. 2 can sync the state to 1, and 1 can sync the state to 2. The pointwise maximum here, this message didn't have any effect on this node because all the nodes are less, all the points are less or equal to the ones here. So 2 is less than 3, so the maximum is 3. Doesn't make any change. So they can all agree that the value is 8. Okay, so could we optimize this? Could this be a bit more optimal? So instead of sending the entire state all the time, we could also send the deltas when appropriate, right? So here comes the delta state CRDTs. And the deltas are also idempotent, have this nice property of, even if I send the message many times, it's okay. The nodes will still converge to the same value. So meaning that if I derive a state 2 from a state 1 joined with a delta, and I do that 2 times, I still get the same state. Really simple. So I do an increment here on a user increments here on node 2. The value goes from 3 to 4. And instead of sending the whole 3, 4, and 2 values, I'm just going to send, because I know this node is in sync, I'm just going to send the differences. And the difference is just the value that I changed, which is 4. Okay? So I send an array with an empty value, 4, and then an empty value. And then you can update just that value, and they're both in sync now. But if a new node number 4 appears here, I will send them the entire state in one go, in one message, right? Makes sense. Cool, so Let's see some JavaScript. So npm install. There's a bunch of libraries that do CRDTs. One of them is YJS. I've used it before. It implements arrays and maps. There's auto-merge, which is really cool. It's an operation-based CRDT that does JSON documents. So you can have arbitrary JSON documents, and they do their best to keep the user data, which is really cool. There's a bunch of them. And then there is a new one I would like to talk to you about, which is called Delta CRDTs. So npm install Delta CRDTs, and let's try and do a quick demo. Let's pray to the demo gods that it works. No, it's not wrong screen. Sorry. Where is it? Okay. I'm going to mirror the displays. How do I do that? Mirror. No. Okay. All right. Cool. I'm Node.js. So I'm going to require library. CRT equals require delta CRDTs. So I'm going to instantiate. Everyone can see this. Okay, so there's a bunch of types here. One of them is the RGA type, with a replicated global array, which is something that is like an array. At the end is an array. Okay, so I'm going to do RGA equals CRDT RGA. So this is how we get a specific type. You can also extend these types, define your own types. So I get an RGA, and then I'm going to create two replicas. Replica 1, I have to pass the ID of the replica, and then replica 2 with the ID of the replica. Okay, never mind. So r1.value is empty, r2.value is empty. Okay, so let's start making some changes. So r1.push, this is like an array. I'm going to push value A, going to push value B. So now, never mind this. r1.value, this is return value. r1.value is AB, as expected. R2 is still empty. So let's push some values here. R2.push C, for instance. V, okay. And D, okay. So R2.value is V and D. Okay, so let's try and sync those. So I'm going to apply. Now, first I'm going to store the state. So state of 2 equals r2.state. So this is the representation of internal state of R2. State 1 is r1.state. So I have both states stored in S1 and S2. Okay. So now I'm going to apply the states to each other. It's like they're sending messages to each other. Okay. So r1.apply the state of replica 2, and r2.apply the state of replica 1. Okay. So r1.value is vdab, and r2.value is vdab, the same. So as expected, cool. So let's do something tricky now. Let's do something like r1.remove at position 0, and r2.insert at position 0, let's say Z. Okay. Okay. So what I did here was remove from R1 the value at 0, and R2 inserted at position 0. So R1.value is right now DAB, and then R2.value is ZVDDAB. Right. So now I'm going to merge those values. So R1.apply R2.state, R2.apply R1.state. So R2.value, R2.value have the same value. So they both converged, and it worked. So this is state-based CRDT. So let's do the deltas. So when you do a change here, like you push r1.push something, for instance, it returns a delta. So let's store the deltas in an array. Okay. So r1. So let's push the deltas 1.push r1.push. Let's say hello OPO.js. Okay. And I can also push something else, OPO.network. Okay. So I can apply those deltas to send those deltas separately to R2. So I can do deltas 1.forEach d, and then R2.apply the delta. So here I'm applying each one of the deltas into R2, and then I can get R2.value is this, R1.value is this, is the same. So I'm in sync. That's it. Any questions? That's it? Yeah? Sure?
Yeah. Would it have mattered if in the example with the counter, if all of the nodes started with 1? Would it have mattered?
Well, they started each one with 1, but they started which one? The sum was 3, right?
Yeah, the total, it was 1, 2, 3, I think.
3. It's the same thing. So you can say, can I repeat? Should I repeat the question? No? No? So yeah, so what would happen is that they would all get the same internal state as a final internal state 1, 1, 1.
Yeah, 1, 1, okay.
Make sense?
And one thing that, just to be clear, the reason you can just send the delta when you're doing the counter with the delta is because you are sure that the node that is sending the delta is synchronized with all of the others because it's in the position associated with itself.
Not with all the others. So when I'm sending a delta to one specific node, I have to know the current state of the other node. Okay?
Yeah, that was my question. How can you be sure that that node is synchronized with you?
You have to have a protocol to know that. Okay. You have to have a protocol to know. So basically, you have an acknowledge protocol. Typically, the paper defines an acknowledge protocol, much like TCP, right? So you can send a bunch of packets, and then it acknowledges a bunch of messages, and then you know which ones to send. If you don't know, the default is to send the entire state to the other peer. Okay? No worries. Have time for more question? No? Yes? Okay. Any more questions? No? I don't. Yeah. Yeah.
I have one.
Yeah.
Do you know of any current big deployment that's using CRDTs to improve the user experience?
Yes, there's a bunch of them. I think SoundCloud uses that for play counts. I'm not sure. There's a big blog post about that. Most React uses it internally, so there's a bunch of CRDTs exposed in the React database, which is a really good fit because they're eventually consistent. So they don't want to provide strong eventual consistency to the clients, which is a nice feature. Other databases, well, and people using React in production are probably using that. Cassandra has also CRDTs. I mean, CRDTs are kind of winning in all these Dynamo-like databases. They're getting there. In peer-to-peer, totally decentralized networks, we are still starting that. So in Protocol Labs, we're doing PeerPad and for collaborative text editing, and people are experimenting. There's a bunch of projects that we're using a different type of synchronization called operational transformations. And now there's a bunch of them starting to adopt CRDTs for that. I know some open source projects that are doing that. But you were asking specifically about the industry?
Yeah, just like you said, like SoundCloud or...
Yeah, there's a bunch of use cases. Mostly backend, because I don't really worry too much about backend. I'm more concerned about the peer-to-peer stuff.
Yeah. Right, thank you.
All right.
Is that everything? Everyone?
Cool.
All right.
All right.
Thank you.